This is the intro for Lab 7 of the Apsc 1299 lab, and we're looking at analog to digital conversion with a sensor. And there is again a pre-lab for this experiment. You should read the datasheet for the reflective light sensor. Hopefully that's going to be on the website. And also read Appendix G on graphing in Microsoft Excel. In Part A, you just need to read through the lab manual and make sure you understand it. But analog to digital conversion is quite an important topic, so do make sure you understand well. I've made an optional video about the theory in Part A, so if you read through the manual, Part A, and it makes perfect sense, you probably don't need to watch that other video. But if it feels like it hasn't quite gelled in your mind, then watch the video because pictures and hand-wavy explanations sometimes do help. So again, in Part A, you just need to read the manual and make sure you understand it well. There is an optional video if you want more information. So our end game in this experiment is basically to make our own voltmeter. We're going to program the chip to measure voltages and then have those voltages displayed on the LCD screen. So in order to test this, we're going to need some well-defined voltages, preferably more than just 5 volts and ground. So for that reason, you've got a voltage divider that you'll be able to use for this experiment. I'm trying to bling it at you so hopefully you can see, but there are 4 resistors connected in series on this board, and they all have equal resistances. So that means that if I hooked up these 2 wires between 5 volts and ground, that the voltage drop across each resistor would be identical. So if this was 5 volts and ground, then the voltage drop across the first resistor would be 1/4 of 5 volts, because there's 4 resistors. And the next one would be another 1/4 of 5 volts, and so on. If I had 5 resistors hooked up in series, then the voltage drop every time would be 1/5 of 5 volts. And if I had 6 resistors, then the voltage drop across one resistor would be 1/6 of 5 volts, and so on. So this gives us some really well-defined voltages, other than just 5 volts and ground, which we can already access. So what you do in Part B is you'll take your breadboard and you will connect the voltage divider between 5 volts and ground. What you will be doing eventually in this lab is you'll have some pin connected via a buffer resistor to a probe wire, and then you'll be able to hook the probe wire into various locations on this voltage divider and measure these voltages. Like I said, that's what you'll be doing eventually. This is basically a pin acting as your voltmeter, and you would display the voltage that you're measuring up on this screen. You're not doing that in Part B. So what you do in Part B, connect your voltage divider between 5 volts and ground, and then grab a real voltmeter. And probably what will work best for you would be to take the alligator clips and hook in some very small pieces of wire, and then use that to probe your circuit. So you'd put the negative end into ground here, and then you could use the positive end here to probe the voltage divider. So again, you can hook it in here, and then measure what the voltage drop between this point and ground is, and then you could shift this wire to another location. So you do that, and you get some accurate values for what these voltages are. Make sure you take good notes in your logbook. By the way, you may see a voltage divider that looks like this. So this is 4 resistors on a piece of circuit board that has conducting rails that run vertically along it. And the resistors have been soldered on there in such a way that the current can go up through one resistor, down through the conducting rail, up through the next resistor, down through the conducting rail, up through the next, and so on in a zigzag pattern. Furthermore, those rails are connected electrically to these pins along the bottom. That means you can put the voltage divider into your breadboard like this, connect up 5 volts and ground, and then to test what voltages you're getting across each resistor, you could take another wire and just plug into each of these sets of holes. So in Part C, you're introduced to the functions you use in order to use the ADC module. So the first one is Open ADC, where you configure everything for your use. The next one is Set Chan ADC. That sets the channel, because there's up to 15 channels you can use for analog to digital conversion. In our lab, we're only going to be converting the signals off of 2 pins. The next one is Convert ADC. This is what actually grabs a voltage off of a pin and starts converting it to a digital value. Busy ADC is a function that returns a value of 1 when the ADC module is still busy with a conversion, and 0 when it's finished. So you can use this function to pause your code until such time as the ADC module has finished what it's doing. Read ADC is where you actually grab the value that the ADC module has come up with, so the converted value. And close ADC shuts everything down. Now, open ADC, as I said, is where you configure everything for your use. This takes 3 parameters: config, config2, and port config. You should read the notes, notes 8, to find out what those configuration should be. It's fairly complicated. And I'm going to scroll down to the next page where there's a bit of code so that you can see how all this stuff works together. So this code snippet comes from sampleadc.c, which you can get off of the website. The first thing they do is they use the openADC function to configure everything for their use. So I'm not going to talk too much about all of these except for the very last thing, 13. So this is port config, and they've set it to 13. What does that mean? Let me go into the notes and show you. So scrolling down here, you've got this chart. So port config can take any value from 0 to 15. And what that does is it configures the 15 pins that could be used as analog to digital converters to be either digital inputs or analog inputs. Now if you chose 15, they would all be set to be digital inputs, and that means you couldn't do an analog to digital conversion. We've set it to 13, and coming across here you can see that almost all of these are set to be digital inputs, and the last 2 have been set to be analog inputs. So that means we can do analog to digital conversions on just these 2 pins. Going up here to the top, you see that those 2 pins are AN1 and AN0. So those are the 2 pins that we can feed a signal into and convert from an analog signal to a digital signal. So now I'll go back to the lab. So again, the first thing they did was use openADC to configure everything. The next thing they do is they insert a very short delay, a 50 TCY delay. The reason why is it takes a certain amount of time after the ADC module has been configured for it to stabilize. So they're just giving it a chance to do that. Next, they go into the while one loop, and the first thing they do is they set the channel to be channel 0, so pin AN0. We also have the option of setting the channel to be pin AN1, but we're going to do that later. So they set it to pin AN0, and then when they call the function convertADC, that grabs the voltage off of pin AN0 and starts converting it to a digital value. This next line is a while loop that is just going to pause the code until the ADC module is finished what it's doing. The next line, they use readADC to return the value that the ADC module just came up with and to assign it to a variable, first ADC value. Next, they set the channel to channel 1, and then they're going to repeat the steps. So when they use convertADC, that grabs the voltage off of pin AN1 now and starts converting it to a digital signal. The while busy ADC line just keeps everything paused until the ADC module is done. And then finally, we use readADC to get the value that the ADC module just came up with, and we assign it to the second variable, second ADC value. Now this snippet of code does not actually do anything with these 2 values. So for example, if you wanted to display these numbers on your LCD, you'd have to add some code in order to do that. And in fact, scrolling down, that's what this next instruction tells you to do. So you're going to display the voltages you got off pins AN0 and AN1, with one signal being on the top line of your LCD and one signal being on the bottom. They also suggest that you display them both as a raw ADC value and as the voltage in millivolts. And by the way, if you're wondering what it is that you're supposed to be measuring, well, it's just your voltage divider voltages. So you would probe the voltage divider in different spots because you know what all the voltages should be, and then you can check whether that's being correctly displayed on your LCD. And finally, the second instruction is just to open up the stopwatch window and to time one of these analog to digital conversions. So we've been using 5 volts and ground as our Vref plus and our Vref minus up to this point, but we know that other values are possible. So in this part of the experiment, you're going to play around with using external voltages instead of the 5 volts and ground that are accessed on your breadboard. So the way in which you do that is when you have that openADC function, you configure it a slightly different way. So for example, you could replace this quantity, ADC Vref minus VSS, with this quantity, ADC Vref minus external. and you would hook up an external voltage to pin 4 to act as your lower voltage reference, rather than using ground, as you have been doing so far. So scrolling down, in the first instruction they say modify your previous code to work with 2 external reference voltages. You also want to modify the part of your code where you're converting the raw ADC value to a voltage in millivolts, because that will also change. Then you're going to use your voltage divider again. You're going to hook up your upper reference voltage to be the second largest voltage on the voltage divider board, and you're still going to use ground as your lower reference voltage. And in the last instruction, you're going to switch things such that your upper voltage is going to be 5 volts, and your lower voltage will be the second lowest voltage on your voltage divider board. So this is one of the robots that we're going to be using in the competition. And the reason why I want to show it to you is that it navigates via these 5 sensors that are all along its leading edge. So in this part of the experiment, you're going to be studying these little sensors. So here's the mount that we put one of the sensors on so that you can study it. So that's the sensor there, that little black dot. It's mounted on a piece of circuit board with the appropriate resistors, and then it's all inside a 3D printed bracket with some wires so that you can attach power to it when you need to. So the first thing you're going to study is how this device reacts when you shine infrared light on it. So it's called a reflective light sensor, RLS for short, and it specifically works using infrared light. There's a little LED on this thing that emits infrared light, and then right beside it there's a sensor. So that means that this device emits light and then catches the reflection. And using that fact, you can detect whether or not you're over top of a dark or a light surface, and the robots use this to navigate an obstacle course that consists of a dark line on a white background. So the resistance of these devices, these RLSs, changes pretty monumentally when you shine infrared light on it. So you're going to test this. You grab a multimeter, and you look at which of these leads is supposed to be positive and negative, and then you hook up the multimeter to it. And what you should see is that you get one resistance value when there's light shining on this device, and if you flip it over so that the light is blocked, the resistance gets much, much bigger. So right now it's about 2.5 mega ohms. If I flip it back over, it's about 0.7 mega ohms. So it makes a huge difference how much light is shining on it. You can, if there's one of these infrared flashlights around, shine it at the device and see what that does. And so this is now at about 34 kilo-ohms rather than mega ohms. Now you notice in what I just showed you that there was no power connected to this. So the LED that emits infrared light, it's not emitting any light right now. I supplied the light either with the overhead lights or with my flashlight. But you can power this guy off of your breadboard. So again, you grab the positive and negative leads and give this guy some power. And I won't plug in the signal wire just yet. But now you should see a little tiny light on the device, on the RLS. And if I cycle the power, you can see that turn on and off. Now what's interesting here is that I cannot see this. This is infrared light. The camera picks it up, the human eye does not. So you can, if you've got a cell phone, actually look at this and see if you can see the light also, although a lot of modern cell phone cameras actually have a filter to weed out the infrared lights. Now at this point in the lab, you've basically built yourself a voltmeter. You've programmed your chip such that it can detect voltages and display them on the LCD. So I've got 2 wires hooked up here for my 2 channels. One of them's plugged into 5 volts, one of them's plugged into ground, and you can see maybe on my display that it's displaying 4,985 millivolts for one channel and 0 millivolts for the other channel. So I'm going to pull out one of these guys and plug it into the board, and then plug my signal wire into the same slot of 5, and so now I can measure directly the signal from the RLS. So in the next part of this, they basically tell you to start playing with this device. So you point it at the windows, you point it at the overhead lights, you write down your observations, i.e. the values you actually got off your LCD. Then you're going to make some more quantitative measurements. So you get one of these grayscale charts. And there is a grayscale number listed on each of these squares. And you'll take your device, your RLS, and you'll place it on each of the squares and write down what voltage you got for each of them. You want to take good notes on this because you need to make a graph of all this data. And in fact, there's two squares on here that don't have a number listed. They're just called A and B. And you put your sensor on top of each of those, record its voltage, and then from your graph, you figure out what the grayscale value should be for these two squares. Then you're going to get data to make a second graph. So you can get rid of the grayscale chart, and you get one of these, which has a black stripe of electrical tape and also, hopefully, a little strip of graph paper. And what you're going to do is you're going to, very methodically, slide the sensor over top of the black line, and then slide it back. And I would recommend taking data every millimeter. It makes a big difference. So you'll move this 1 millimeter at a time, record the voltage you get, all the way across and then all the way back. And you put both of those sets of data on the same graph, and you have a look at them. What you should see should roughly look like a step function, where it goes up when it's over top of the black and then back down when it's over top of the white. And what you're going to look for is what would make a good threshold value, a number for the voltage that tells you that you are definitely over the black line now, because this would be useful for you when it comes to programming your robot to be able to follow a black line, is you need to know what threshold value tells the sensor that is now over top of the black line. So just to reiterate, by the time you get to the end of this part of the experiment, you will have two graphs made, which should go in your logbook.